Yeah, so thanks for coming to my talk. Can everyone read the screen okay? I've got a live demo later, but the screen is completely whacked on my laptop, so that will be quite interesting, but it looks okay up there. So yeah, I am Fraser. I do work at Red Hat on cryptography things. I'm not a cryptographer, but I apply cryptography to accomplish security, hopefully in a manner that is actually usable. So here's a story, right? A machine in a data center gets rebooted, needs to be patched or whatever, and the machine has full disk encryption. So when it comes up, requires a passphrase to decrypt the key encryption key and proceed with booting the system. So how does this happen? So there are a couple of ways. The first way, this is the way normally if you have a workstation with full disk encryption, is that you just type the passphrase in and off you go. In a data center, you don't really want to have to be burdening administrators with logging into the system, or worse still, going down to a data center and punching it into a terminal. So maybe you implement some sort of key escrow solution. This may not be ideal because then you have the secret residing in a separate system. So that becomes a high value target, particularly if there are many secrets stored in the escrow system. So this is a bit of a problem. Or another story, a network daemon that uses TLS gets restarted. So it needs to get access to the TLS, or the private key that it's using for TLS. So it too needs a passphrase to decrypt it. Or does it? Well, there's a proliferation of advice on the web with people saying, oh, I want to reboot my Apache, but it always prompts me, how do I get around this? And usually the top answer is something like, oh, you just do OpenSSL RSA and put the password in and then save the unencrypted file to the disk and off you go. So you've got your raw private key just sitting around on the disk to be read by anyone who gets access to the system. Not a good idea. Again, maybe there's some sort of escrow system that could be implemented here. Yeah, or logged in administrator types it. So what do we actually want? What are our goals here? Well, we want the secrets to be stored at rest. So if our disk fails and we have to send it back to the manufacturer, or if someone walks in pretending to be from IBM and walks out with a rack of servers from your data center, they're not going to be able to read what's on those disks. Just common, baseline security practice here. But we do want automated decryption of secrets when the servers are where they're supposed to be. So if you have your laptop and you come to the office and you're on the corporate network, maybe you don't want to have to put in your passphrase. Maybe we can just decrypt that automatically, and it'll save you time, which saves the company time, which saves the company money. And it also avoids kind of the password fatigue of having to type a password in over and over again. And if it is a secure password, you're going to have lots of special characters in there, so the possibility of typographic errors is quite high. So we call this concept binding the secret to the network, right? So we want to be able to acquire or decrypt a key when we have access to a system or a set of systems on a secure network. And when we're not on that network, or if the machine is taken out of that network, or if the disk is removed from that setting, then no one should be able to decrypt its contents. Now, another important goal is that the secret is never divulged to a third party. So we don't actually want to implement an escrow solution where we transmit the secret to another party, be it still a machine in your organization or perhaps not, and say, hey, here's my secret, can you please look after this for me, and when I come back and authenticate to you later, send me back the secret. So the secret is going to go through a presumably encrypted tunnel, but you still have another party that knows that secret. It's a high value target if it knows a lot of secrets, And it's a high-value target if the information secured by that secret on your system or on the client system is of high value. So we want to avoid this situation as well. So there are some assumptions. The assumptions is that in this kind of secure network context, the network is in fact secure, that your physical machines are secure, and that the secret is going to be safe in memory. So obviously we know that's not always the case. That's not actually the problem we're trying to solve here today. So application security is important, but that's a different problem. So yeah, we're going to talk a bit about cryptography now and the cryptography of this solution. So Diffie-Hellman exchange, can I just see a show of hands who is familiar with Diffie-Hellman? The details thereof, most people in the room, which is good. So it's a secure key agreement protocol where two parties can agree on a shared secret without a third party being able to learn what that secret is, with an eavesdropper, for example. Diffie-Hellman on its own doesn't provide any authentication, so it's just a way for two endpoints to basically get a secure tunnel between them that no one can eavesdrop on or modify information in. So Alice and Bob can agree on the secret. This is just the names that we commonly use in cryptography. Alice and Bob for two parties and Eve for an eavesdropper. Integrated encryption scheme is an encryption protocol or algorithm based on Diffie-Hellman. It's kind of similar to Algomal, but in Algomal you map a key into an element of a group, and that mapping is reversible. So in the end, when you get that group element back, you can reverse the mapping to get the symmetric key. IES computes the shared secret and uses a key derivation function to derive a symmetric key. So yeah, basically Alice encrypts a message to Bob, sends the message to Bob, and only Bob can decrypt that message. So, and here we come to the new cryptography, the McCallum-Raleigh exchange. So Nathaniel McCallum is a colleague of mine on the identity management team at Red Hat. Well, he works in Raleigh, North Carolina. And Bob Raleigh is a cryptographer. He also works at Red Hat. So Nathaniel had an insight and basically discovered a kind of double encryption algorithm and worked with Bob Raleigh to refine that algorithm into what we now call the McCallum-Raleigh exchange. So in McCallum-Raleigh exchange, Alice, just like with IES or with Algomal, encrypts a message to Bob's public key. But she doesn't send it to Bob. She just keeps this encryption and then throws away her private key, so it can't be decrypted with the information that resides on disk. To decrypt, Alice then asks Bob to encrypt a related key, which is an ephemeral key, so it's randomly generated on the spot. And a different one will be used for each decryption cycle. And then she can use the reply from Bob to decrypt the secret. So Eve can't decrypt the secret, and neither can Bob. Bob can never learn what the secret is. So this accomplishes our goal of having a way to compute or acquire a key without any other party learning that key, yet the key can be stored securely on disk. So how does this work? Algomal and IES are what we call malleable cryptography, which means that you can perform some transformation or some function on a ciphertext, and that transformed ciphertext will decrypt to a plain text that is related to the original plain text. This is a highly undesirable property in most cryptography, but it's an essential aspect of how Algomal and IES and incidentally McCallum-Raleigh exchange work. Now these operations can be performed in a variety of groups where there's a hard problem. So the most common ones are the integers modulo p with the multiplication operation, so a multiplicative group of integers, or elliptic curve point factorization in an elliptic curve field. The discrete logarithm in the integers modulo p, these are hard problems. And that's what the security of the cryptography is based on. So you can actually do this algorithm in any cyclic group with a hard problem. And yeah, as I mentioned earlier, the concept is that you can double encrypt a secret, send the secret to Bob. Bob can decrypt the related plaintext, but he can't learn the actual shared secret from that plaintext, sends that result back to Alice, and then Alice can use that to compute the shared secret, which isn't actually shared. Alice has shared it with future Alice. So what else do I have to say about this? No, I think that pretty much covers out that slide. Okay, is everyone following along? Okay, I'm going to kill you with math. So the parameters for Maclaurin value, as we're using it in our software, we're using the elliptic curve variant. You can do it in integer groups. So you have an elliptic curve field f of size q and an elliptic curve on that field. We have a base point or a generator g, which is a point on the elliptic curve. And we also use a key derivation function, incidentally, PBKDF2, and a symmetric encryption algorithm, ENC. Again, incidentally, we use AES GCM. So the encryption phase, what does that look like? Well, first, Alice generates a private key by just selecting a random element from the group. The server also has a private key. Now, Alice's private key, this will be different for every secret. She can generate a new one for every encryption. Bob's, or the server's, private key and public key never change. So that stays the same. Well, you can't, there are key rotation provisions in the protocol, but you encrypt to Bob's public key so that key pair can't change in order to be able to perform the decryption. If Bob throws out his private key, then there's no way to decrypt the secret or compute the secret. So in the encryption phase, the client will acquire Bob's public key or the server's public key, and will then compute the shared secret by raising Bob's public key to Alice's private key, and then performing the key derivation function on that to acquire a symmetric key. So the shared secret is actually g to the power of a times b. And then having acquired the symmetric key k, or computed the symmetric key k, Alice saves her public key and the ciphertext, which is just the encryption of the message m, with the derived key k. So that's the encryption phase. Nothing gets transmitted to the server at this stage. We only read information from the server, and this can be done offline as well. For example, you could include, the public key for your infrastructure as part of a corporate standard build image, or so on, so that the provisioning phase can occur without any network communications. For decryption, Alice generates a new key pair, or a new private key x, and computes the value x, which is a, her public key, times g to the power of x. By the way, when I'm talking about exponentiation here, in the integer modulo p group, it is actually exponentiation. In elliptic curve groups, it's a scalar multiplication of elliptic curve points. But I use this notation because it's, I think, probably the most familiar notation when discussing these sorts of cryptographic algorithms. So the value x is g to the a times g to the x. The client transmits that to the server in a decryption request, and the server basically encrypts this with the server's private key, so capital B here, which results in this value, x prime, which is g to the ab times g to the xb, and transmits x prime back to the client. And then this value here, x prime times the inverse of b, Bob's or the server's public key to the power of x, actually works out to the secret that we performed the original key derivation with, g to the ab. and then we can perform the decryption with this derived key to obtain the original message. So that's how that works. Are there any questions at this point? Okay. All right. So that's the end of the math for now. So I'm sorry you can't see that. Tang. Tang is the name of this protocol. We'll get to why it's called that in a little bit. So Tang is both a server-side daemon, that's the server component, and a clevis pin. What is clevis? What is a clevis pin? We'll get to that in a few slides as well. It's written in C, it's got an extensive test suite, it's really fast and quite a small code base, and it's nearing stable release. So I can't tell you exactly, well, you can go and run the code now. I can't tell you exactly when it's going to be in some sort of supported product from my employer, but hopefully one day soon. The protocol itself is UDP-based. The messages are DER serializations of as and when objects. There's no encryption because there's none needed. It's basically a key agreement protocol where only one side learns the key. And it's trust on first use in its current form. So basically, the server also has signing keys that it uses to sign its responses. It can sign with multiple signing keys. This allows key rotation. And it is possible to implement out-of-band key validation. So you might want to use like DNSSEC DANE records or something to store the fingerprints for your Tang servers so that you don't have to have the clients manually check a fingerprint before proceeding with the encryption or the provisioning phase. The threat model there is simply denial of service. There's no risk of disclosure of the secret to the server because the protocol prevents that. But a malicious party pretending to be your corporate Tang server, for example, could advertise a public key where the corresponding private key has been discarded, for example, and then that would mean that the secret that has been encrypted will be forever unrecoverable. So it's just a denial of service attack that the trust model prevents. But of course it is trust on first use, so there is a vulnerability there if people don't validate the signatures or the fingerprints. Yeah, so threats and caveats, the man in the middle on the first use could cause the client to encrypt a bogus recovery key, which means the secret is unrecoverable. It also means that a single Tang server is a live DOS target. So if you can take the Tang server offline, the ability to automatically decrypt the secrets or the keys goes away, and you fall back to having to type in a passphrase or some other mechanism. You need good entropy early in the system, or you need good entropy for X. If you're dealing with full disk encryption, for example, you're going to need good entropy early on. And quantum computing, yeah. So if you were in the previous talk, you know that quantum computing presents a risk for hidden subgroup problems like the Diffie-Hellman assumptions and whatnot. So, yeah, if practical quantum computers that can run Shor's algorithm appear anytime soon, then all of the usefulness of what I'm showing you just flies out the window. So the history of this project, the DAO project began about a year ago. It comes from the Greek dao, to bind, and it used TLS for securing the key in the tunnel and X509 encryption certs as well for encrypting the secrets, which resulted in a lot of deployment complexity. I don't mind X509, I'm kind of a PKI guy, but the new protocol is definitely much easier to deploy and much simpler. So in DAO, in the original implementation, the server would, you could encrypt this secret yourself using the server's encryption certs. But to decrypt, you had to send the encrypted blob to the server. The server would decrypt it, thus learning the secret, and send the secret back through the TLS channel. And this violated one of the design goals. But we hadn't discovered a better way to do it at that point. That happened in September 15, when Nathaniel McCallum had these insights, and then the algorithm was refined into McCallum Value Exchange. And so we killed Deo with fire and started again from scratch. And then in December, we split the project into two projects, Tang and Clevis. So on to Clevis now. So if we can bind a secret to a network, we might ask, well, what other sorts of things can we bind a secret to? And the answer to that question is things like TPMs and smart cards, maybe a Bluetooth LE beacon or some other sort of system that you can communicate with, but not over an Ethernet network. Biometrics, like maybe you can scan your face and derive some sort of secret from that, or your fingerprint or your voice or whatever. Or a master unlock key in an organization. So if you want to have automatic decryption of the laptops, but if your Tang servers are down or if the users forget their passphrase, maybe we want to be able to bind to kind of some sort of escrowed key that can unlock a particular system or unlock all systems within an organization. It's going to be secured, stored very securely in a bank vault or whatever, I'm sure. So we come to the question now of unlock policy, right? So security is not binary. It's a sliding scale of risk and convenience. And it shouldn't be up to the technical programs that we use, the software that we use to determine what the security policy should be. But rather, the organizations or individuals should determine their security needs, and hopefully the software can conform to or implement the sorts of policies that organizations want when it comes to security. So how can we support arbitrarily complex unlock policies like, for example, if you follow through me with this, you can't see the laser pointer. So maybe at the first stage, we want to have user passwords, a Tang server for decryption, maybe a smart card that can also be talked to decrypt or negotiate a secret, and maybe your fingerprint as well. Maybe we can derive a secret from that. And so we say out of this set of possible secret acquisition sources, we want 2 or more to unlock the secret. And then we say at stage 2, well, once we've unlocked stage 1, we also want to bind to the TPM. So if the disk has been removed from the server or the laptop, well, we'll talk about a laptop because this looks like sort of a workstation policy. If the disk has been removed from the laptop, then obviously the TPM is not going to be present, so we don't want them to be able to decrypt the contents of the disk. So in this case, we want both the result of stage 1 and the TPM. And then finally, the unlock, we want either stage 2 to have succeeded or another password, which might be that organization-wide master password or some master password for this system that's been escrowed by the organization as a last resort. So that when you call in and say, hey, all the stuff's broken and I can't get into my computer, then they can still unlock it. So this is just a made-up example, but this is the sort of policy that we want to be able to support when it comes to unlocking disks or unlocking secrets. So the way we can do this is with an algorithm called Shamir's secret sharing. The idea behind Shamir's secret sharing is that you can describe a polynomial of degree k-1 using k points. So, for example, 2 points describes a straight line, a linear function. 3 points uniquely describes a quadratic function. If you only have 2, that describes infinity quadratic functions, because any number of quadratics could go through those 2 points. So if you want to have a threshold of n, or threshold of k for unlocking a secret, then you come up with a polynomial of degree k+1, and then you set the free coefficient to the secret. So if all of the other coefficients are 0, then the result of the function is going to be the secret that you want. And then you can distribute n, you randomly select all the other coefficients. Then you distribute n points on this function, as long as n, as long as x that you distribute does not equal 0, because that is actually the secret, the value of the function at 0. So you can distribute n where n is greater than or equal to k. And then all you need is k of those secret shares to come back in order to compute the original secret, and the way that's done is with Lagrange polynomials. So as an example, here is a secret with a threshold of 4. Well, it's not a secret, this is just a Lagrange polynomial, but the way it works, the dotted line is actually the polynomial that these 4 points, which are the blobs on the lines, describes. So given these 4 points, you can compute the Lagrange basis polynomials, which are the coloured lines, and then the sum of those basis polynomials is the interpolated polynomial, and then evaluating the interpolated polynomial at 0 gives you the secret. So Clevis is a client-side pluggable key management system based on Shamir secret sharing. The plugins are called pins, and we have plugins currently for Tang, password, and HTTPS. So it's just where you put the secret to an HTTP server, HTTPS, and then when the acquisition phase occurs, we just do a get to get that secret back. It has JSON configuration and very few dependencies. So OpenSSL and libjanson, and libcurl if you want to use the HTTPS pin. The terminology is based on a simple kind of shackle. We got the Tang, which means tongue, and the Clevis kind of housing, and a pin goes through them, and that's it. That's how it's shackled. That's where the terminology comes from. So I think that's enough math. Demo time. So how am I doing for time? I think maybe another 10 minutes maybe? Yep, brilliant. Okay. This is going to be tough because my display is pretty out of whack. Okay. Just make that slightly smaller. Whoa. Okay. So, yeah, okay, can people read that? Yep, that's not too bad. Okay. So, the first thing we'll do is we're just going to have a password-based, so policy with a single password. So we'll do a Clevis provision. Just going to make sure I'm spelling that right. Dash capital P for the pin config. It's a JSON object. The type will be PWD, I think. Yep. And I think that's all we need. Okay. Oh yeah, that's not all we need. Dash capital O. So we're going to write a resulting metadata file. We'll just call it pwd.json. Okay, so it's asking me for a password now. Okay, and it spat out the secret. So it actually generates a random secret. And at the end of the acquisition phase, it tells us what the primary secret is. So if you want to encrypt something with that secret, you can then take that and use that as the key. To acquire this secret, run Clevis acquire dash capital I, input the meta file, that was output, and ACQ, I can't spell acquire. Oops. Sorry, I really cannot see anything on my laptop screen. Okay, so it's going to ask us for the password If I put the wrong thing in, it's just going to ask again. Actually, there's no way to kill it, but there's a ticket for that. But, whoops, I've given away half my password. Luckily, I did still remember the password, so I was able to successfully complete the acquisition phase, and you can see it's returned the same password as before. Okay, so now let's do something a little more interesting. Let's have a tang pin. So clevis provision pin config type tang, and we also need to tell it where the tang server is. So we have a host parameter. There's a tang server running on localhost, so I'll just use it. Oops. And -o tang.json. Okay, it's going to show us the keys. So this is that trust on first use negotiation occurring here. Yeah, I'm going to trust them. And once again, it spat out the secret that was encrypted by this process. If we have a look at the metadata, well, that might less that. Okay. So you can see it's saved. Right. So this is the contents of that metadata file that is spat out. You can see it's saved the name of the pin, the port and the host name of where the tang server lives. This is the advertise response. So this is the DER encoded, or base 64 encoding of the DER encoded response from the server that contains its public key as well as its signatures and signing keys. This is the ciphertext. It includes the PB KDF2 parameters as well as the ciphertext, and OIDs for the KDF in use. I think we'll need to be adding an OID for the cipher in use as well, so that we have some agility if we need to move on from AES GCM in the future. And recovery. I can't remember what this parameter is. Anyhow, we'll do an acquire. So clevis acquire -i tang.json. I need to get out of that. Okay, brilliant. So it's acquired that with that McCallum Rally exchange with the tang server. But now if I kill the tang server and try to acquire, it's just going to quit because it couldn't talk to the tang server. I'll just start that tang server back up. Okay. And now we'll do a Shamir secret sharing. So we're going to do one with password and tang with a threshold of 1. So we'll do a clevis provision -o sss.json pin config type SSS threshold 1. Pins, and we'll have an array of nested pin definitions. So this one will be type password, yep. And another one, type tang, host, localhost. Okay, it's going to ask us for the password, and it's also going to do a tang provision. Yep. So it's provisioned 2 shares in the SSS secret, or the 2 shares, yeah, of the polynomial, basically, and it can use SSS to recompute them if either one of those sub-pins succeeds. So if I kill the tank server again and run clevis acquire -isss.json, it's going to ask us for the password. Okay, let's put the password in. Sweet. There's the response. Oh yeah, that's fine. But now if I do the acquire again with the tank server running, there we go, so we didn't have to put the password in. So if you can imagine this running at boot time, it's just going to take a moment while the tank thing goes on in the background, and then just continue with the boot without any user input, assuming the machine can talk to the tank server, i.e. you are on your secure corporate network. Now, we did have early boot integration working in DAO, but we haven't implemented it yet for Tang and Clevis, for Clevis. But to prove to you that we did have it working, I'm just going to show you some DAO code now with the boot integration. So you can see this one was using full disk encryption. I had to enter the passphrase to to boot the system. I'm going to reboot it in a moment, but before I do that, I will start a DAO server. So sudo system control start DAO decrypt D DRCYP. Yeah, okay, so it's running now. And if I reboot this machine, oh crikey. There we go. Restart. So we'll come back to that in a moment. Hopefully we'll observe. That is working. So I hope you enjoyed the demo. Yeah, as I say, we'll come back to that in a moment, and hopefully we'll observe that the DAO decryption did work with the early boot integration, but as I said, we haven't gotten there yet with the new project, Clevis. Okay, so what's the status of Clevis? Clevis is less mature than Tang. It's still under active development. Early boot integration is a high priority. Key rotation is not implemented yet, but the protocol supports it. Resources, we got the Tang and Clevis repos. They're both written in C. They're not too bad to work on. I've submitted a bunch of fixes to Tang. Clevis code is pretty clean as well. The DAO wiki, so the third link down, actually contains most of the information about the use cases and the new algorithms, because it was still DAO before we split the project, and we just haven't copied that information across. Also, the Tang and Clevis repos are soon going to move into a GitHub org, which I believe is called, if I remember rightly, latch set. I also have a blog post on the Apache integration, which I haven't shown you, but if there's time, I can. But maybe it would be better to go to questions first. Oh, no, hang on. I'll one or two more slides. So how can you help? If you're interested in helping in this initiative, please review the cryptography. Bob Raleigh is a cryptographer. He knows what he's talking about, but more eyes are better. So if you are interested in helping our efforts and you are a cryptographer, please review our algorithms. Protocol review as well would be great, and code review. And testing, be like me and test some of this code and find the bugs. I think I'm probably one of, between Nathaniel and myself, maybe the only two people who've actually used this stuff in Angular yet. And you could contribute Clevis pins. So if you know a lot about DRM programming or biometrics or something, maybe you can write a pin to acquire secrets via these technologies or mechanisms. Okay, that is the end of the talk. So we'll just see if, and you can see it hasn't prompted us for the encryption passphrase, so the DAO decryption succeeded there, just to prove that early boot integration is a thing that we can do. So, on that note, any questions?